Hopefully everyone can hear me clearly, but I'll start my quick little show. So here, for a brief little bit about me, I'm from Los Angeles, California. I got a BA in Geography and History from University of California, Santa Barbara, UCSB. I'm currently an MS Geography student at SDSU. I teach the Geography 101L Earth's Physical Environment Laboratory course, and my research interests are remote sensing, 3D remote sensing, GIS, etc. But as we mentioned actually previously, one thing I want to note is that way back in the day of about 2012 or so, a long time ago, I was your age in 9th grade in a geography course in high school. I believe we have a 9th grade class here, if I recall correctly. But it was a geography course in high school that I believe set me on the path of liking geography. So just a little fun note that I saw. But anyways, so a bit about remote sensing. I think this might have been touched on a little bit beforehand, but it's something key to my research interests, so I just want to touch on it briefly. Remote sensing is, to quote, the collection of data about features or phenomena of the Earth's surface and near surface without being in direct contact with the features or phenomena. Or put in more simple terms, it's using cameras and sensors of various types, everything from radar and lasers to, normal image cameras of all sorts and types, to learn more about the Earth. This can be whether it's on, as you can see here, either it's on a satellite or, a UAV or a drone, which you probably heard about these days, or an airplane or a very long pole or a ladder or a kite. Kites are a fun platform. But as remote sensing, trying to learn about the Earth without, being right next to the thing you're trying to learn. You're not digging holes in the ground, that kind of thing. So my research involves three-dimensional remote sensing in shadows. Three-dimensional remote sensing is just 3D, so it's not 2D flat, it's 3D. So you have 3 dimensions, length, width, and height. Goodness, that's not quite how all things work, but so this includes ways to get this includes LiDAR, photogrammetry, structure from motion. What you end up getting is a 3D representation of the world. It's kind of like a video game where you have, as you can see here in this image, we have shadows and the like. It may look flat, but you would be able to rotate this and see different perspectives and the like. So what I'm trying to do is we're working on a project to detect changes in vegetation. So, see vegetation grow over time. But, which would be pretty useful if you think about it, because you could then very easily measure how vegetation grows. One issue we found is that, as you may see in this bottom right image, shadows can be troublesome. Not to get too much into detail, but the blue and the red colors indicate changes from one time to another. And you can notice that a lot of shadows changes get detected, which we would prefer to avoid. So my current research work is trying to detect and classify and then remove the shadows and imagery from a UAV, specifically that one I actually showed previously. So in the top right there, we have an aerial image here from a UAV. And then in the bottom, after a fair amount of processing and tools, which I definitely won't get into details here, we have this image, which is just 2 things, shadow or not a shadow. So if you, for instance, look, say, here on the top image, you can see shadows here. It's still a work in progress, so we don't have everything. But if you say, look over here, you can see the shadows are more purple, while the non-shadows are less purple. Still a work in progress, as always, so it's not perfect. But that's a general goal, use this sort of stuff to detect fine shadows. It's certainly really interesting, and there's a lot to do. But one thing I'm also working on recently is I'm trying to organize the process to make it more clear, because before it involves a lot of different programs and tools and the like. So I'm currently working on trying to use programming, specifically the Python programming language, to put everything together in one form. So not to be one of those people who says, oh, programming is the future of everything. I certainly wasn't until I started doing some work with Python, but it can be really handy, particularly for geography work. Like on the right here, I have some work I did for a course I'm taking. wherein I have code that took a bunch of addresses, kind of searched them in online, like in Google Maps or MapQuest or like, and then mapped them out with these little points using the code mentioned there. So it can be really handy stuff. And if you're interested in geography, it might not hurt to try learning a little bit of programming. And I think there's a fair amount of free resources too, in case you ever wanted to give it a try. But anyways, that's enough about my research work. One other thing I wanted to speak about is Geography 101L, which is, it's the class I teach. It's an introductory lab course about physical geography. So we get a fair number of, freshmen and the like. So if you go to, if you take geography courses in undergrad in your freshman year, this will probably be the type of course you'll take in many places that you go to. So this class, we talk about stuff like solar radiation, continentality, hydrology, map reading, biogeography, a little bit of remote sensing, and more. Just for one quick little example of something we cover in this class, there's a website called USGS Earthshots, which highlights interesting things you can see from remote sensing satellites. So here we have an image of Mount St. Helens, Washington on September 15th, 1973. So if I just asked in general, what sort of seems to be in the question, what would you say? Nothing strict, but just, what sort of appears in the image. One thing to note is that it's a false color image, which is basically a fancy way of saying we've changed normal colors. So in this image, plants and vegetation are red. So yeah, take a guess. You can write out in the chat. I'm not grading you on anything, so just a fun little question.
Guess they don't know Mount St. Helens.
Well, if we go to the next slide. So here's Mount St. Helens 10 years later on May 22nd, 1983. What seems to have changed from the previous image? We have previous image, next image, previous image, next image. What seems to have changed? A lot more red? Yeah, the colors have changed. So in the first image here, there's a lot more red in certain areas close to the mountain and less elsewhere. But then afterwards, there's a lot more red around the mountain, but nothing near it. So if you guys don't know, in 1983, Mount St. Helens, it's a volcano and it erupted in 1983. So what you're seeing here in all the gray is volcanic ash and debris spreading out across the landscape. So it's pretty cool you can see this from space, but you can. It's a really good way of measuring, say, how much volcanic ash went out. So, and then the next one here is Mount St. Helens, Washington on August 23rd, 2020, which is, about 40 years after the previous image. So can you sort of guess what may have happened after the eruption? Again, this image is in false color, so all the vegetation is actually red, not green. Yeah, the volcano, it came through, killed a lot of plants. But then over the years, into 2020 here, the plants have regrown. Yeah, you can see here we have, for instance, let me draw a quick little line here. You see this green line here is kind of the boundary of the volcanic eruption. If I go forward, you can see now the boundary of the eruption is here. And so vegetation is growing back closer to the mountain again. Cool things you can see with remote sensing. So one last thing I want to add is I have a neat little page here with lots of resources and sites I've used in the course. This includes USGS Earthshots, where I got the those images from. There's also the NOAA solar calculator, which lets you see solar angles and the like. It's kind of neat. There's also Science in Your Watershed, which helps you learn about your watershed, which is how water flows where you are. And there's also USGS Topo View, which lets you see lots of cool old topographic maps of your area. And that's it. So thank you for listening. Hope it's been interesting. Any questions before we continue? If we have the time to continue, that is.